Hello students, good evening all. So welcome back to our next session of topic sequences and series. So far we have finished with our arithmetic progression and we are now dealing with this geometric progression. So before starting our today's session, so first we'll just have a quick recap of the topics that we have covered in our previous session of sequences and series, as well as we'll just have a brief introduction to the topics that we are going to cover in our today's session of sequences and series. So in the previous session, we have already discussed about this arithmetic mean. So where it is generally represented by capital A, and if we have to find the arithmetic mean between any given two numbers, it is given by capital A will be equal to A plus B by 2. So this will be the arithmetic mean. Right, and then we have seen for this inserting. So the new concept that we have learned with respect to this arithmetic mean is inserting some n arithmetic means between given two numbers. Right, then the sum of those inserted arithmetic means, that is sigma ai, where I will be from 1 to n. So this sigma, this sum of all these inserted arithmetic means is given by capital A into the number of inserted arithmetic means. So where A here we have already have the value for A, which is given by the two numbers average, where we have inserted this n arithmetic means. So after this arithmetic mean, so with that we have almost finished our arithmetic progression concept, and we have started discussing about this geometric progression, where we have seen the typical introduction, like the definition of this geometric progression, as well as the terms and terminology which are involved in this geometric progression, and the nth term or the last term of this typical geometric progression we have seen, and we have even seen the general representation of this geometric progression, which is given by A, AR square, and so on until A r power n minus 1. So this is our general standard form of geometric progression, where the last term here, that is the general term Tn, is given by A into r power n minus 1. So this and all we have discussed in our previous session of sequences and series. So coming to our today's session, we are going to start with this series of GP. So as we know that what actually meant by series, so we are familiar with this series, so which is nothing but the sum of all the terms which are present in the sequence. Right, so that's all. So this is our standard GP, and we have to do the find the series of this GP. So we are going to start our today's session with this series of GP. And after this series of GP, we are going to discuss this properties of geometric progression. So there are few and important properties which are related to our geometric progression, so that we are going to have a look here. And after that, so with this properties and series and all, we almost finished. After this, we are going to discuss our geometric mean, how we have discussed our arithmetic mean. Similar way, we are going to see the geometric mean, GM. And after that, we are going to see the relation between our arithmetic mean and geometric mean in our arithmetic progression and the geometric progression. So the typical relation between them. Right. So, and after that, we are going to discuss our AGP. So AGP is nothing but a combination of our arithmetic progression as well as the geometric progression. So which is called to be arithmetic geometric progression, which is the AGP here. So first we are going to, sorry, you are here. So first we are going to start with this series of GP. So if while discussing the class, if you are guys having any questions, any doubts, you can please let me know in the comment section. And if you want me to go slow, that also you can mention, so that I'll just follow up by that. So let's start our today's session with this series of GP. So in our, we have the standard form of GP, which is given by AR square, AR power n minus 1. So the sum of all terms here is nothing but AR plus AR square, and so on, AR power n minus 1. So here we can take r common, and then we'll be having 1 plus r square and so on, r power n minus 1. Right. So with this, it is also in GP again. So here you can see, so there is a multiplication and subtraction terms here. So without that, we can directly say that here our Sn of this sum of the terms, n terms of this geometric progression will be equal to this A into 1 minus r power n by 1 minus r. So this will be the sum of n terms, that is the first n terms of a geometric progression. So in and simple, we can say that our Sn will be equal to A, which is the first term of the geometric progression, 1 minus r power n, where r is the common ratio of the geometric progression and n is the number of terms which are present in this geometric progression, divided by 1 minus r. So this is the generalized formula which we are going to apply and use while discussing and finding the sum of the first n terms of a GP. Right. So here when we trying to discuss this sum of the terms, so there will be a special case, because here our general standard form of geometric progression will be in the format of AR, AR square, R cube until AR power n minus 1. Right. So here our sequence of this geometric progression will be depending upon this common ratio. So depends upon the common ratio, we'll be having our sum of the n terms for this geometric progression. Right. So let's discuss the cases here. So the first case is when the common ratio is equal to 1. So what happens to the geometric progression when the common ratio r value is equal to 1? Then every term which is present in this geometric progression will be turning out to be a comma and so on until a n times. Right. So when we do this sum of all these terms when r equal to 1, then what will be the sum of the first n terms here? That is Sn will be equal to a plus and so on n times, which is given by n into a. That means when the common ratio, that is the r value, when it becomes equal to 1, then directly we can say that the sum of the first n terms of the geometric progression will be equal to n into a. So the same condition even in our arithmetic progression where the common difference becomes 0. So when common difference becomes 0, the progression, the sequence will be the same term will be repeating. There also the sum of terms will become equal to n into a. Right. So the next one here that we are going to discuss is when the r less than equal to 1. So less than 1. That means our common ratio less than 1. Right. So what happens when r is less than 1? So for suppose, let me take 0.01, which is less than 1. This is my r value. So if I substitute my r value here, for r, it will be okay. R square, okay, it will be 10 power minus 4. What about r cube? What about r power 4? R power 5? So it will be very, the value will be reducing. So such that it will become finite. Right. So it will become very small that we could neglect that r value. Right. That's why when this r is less than 0, the common ratio is less than 1, then we will be having our sum of the n terms will be having a finite value. So the sum becomes here a finite value because we will be having r which is less than 1, which means it is in terms of 0 point something. When we take it as r, that will be fine. If it is r square, then it will be 0.0001. What happens if it's r power 4? It is 0.00000, which is we can neglect when the power of the r increases. Right. So that's why the sum here will becomes finite when the r value, that is the common ratio value, is less than 0. Right. So that we have to keep in mind, and that will be our sum of, the next will be here the sum of the infinite term. That means when r will be less than 1, we will be having the finite terms. Then that sum will be given by, so let's see that. So what is our general sum of n terms that we have seen? Sn will be equal to a into 1 minus r power n by 1 minus r. So just now we have seen in our previous slide, which is given by Sn. When our r is less than 0, our terms will be tending to infinity, which we actually eliminating that. That means here our n will be tending to infinity. So let's apply our limits concept here. So I think you guys are not familiar with this limits concept now, but we'll be having a separate chapter, limits and continuity. So there you'll be having a quick idea over this limits and continuity topic. So far we'll just take that as our r power is increasing, we'll be having infinite terms where we can neglect it, and that will make us our sum of the n terms will become finite. Right. So that's why here the n will be tending to infinity. So let's apply that. So Sn, where limit n tends to infinity equal to, so this side it will be n tends to infinity. So that is 1 minus r power n by 1 minus r. So if we substitute this infinity, so this will become 1 and this will become 1. So this term can be rewritten in another format, that is limit n tends to infinity a into r power n minus 1 by 1 minus r, because we just rearrange the terms. Right. So then when it comes to limit n tends to infinity, that will be 1 and here this will become 0. Right. So either of the way we'll be getting anyways a here. If it is a into 1 minus r power n, so this will become 0, which means a into 1 minus r here. So this will become minus 1. So which makes it 1. So here if it is r power n minus 1, so this will become r power, when it tends to it will be 0. So it will be equal to our s infinity, that is when n tends to infinity, sum of infinity, the sum will be equal to a by 1 minus r. So far we have seen 3 formulas for our sum of the terms in our geometric progression. First one is our Sn will be equal to a into 1 minus r power n by 1 minus r. And the second one, when r equal to 0, our Sn will r equal to 0, 1. Right, when r equal to 1, the Sn will be equal to n into a. And the same thing when r is less than 1, that means sum of the infinite terms. So we'll just make it as the sum of infinite terms, that is s infinity is given by a by 1 minus r. So these are the formulas which are related to our sum of the terms which are related to the geometric progression here. Right. So after this series of GP, so let's have a look over the properties which are related to GP, and then we'll just go ahead and start solving questions related to our series of GP. Right. So if each term of a GP is multiplied or divided by the same non-zero quantity, then the resulting sequence is also GP. Right. If for suppose we are having a GP sequence AR square, r power n minus 1. I am just taking the standard form of GP. Right. So if this each term of the GP is multiplied, either multiplied or divided by same non-zero quantity. So the condition here, the quantity should be the same as well as it should not be equal to 0, which should be a non-zero quantity. So let me take 2, easiest value. So I am going to multiply 2 to each and every term of this geometric progression. So then my progression will be turning out to be 2a into 2ar into 2ar square, 2ar cube, and so on until 2ar power n minus 1. Right. So now this resulting sequence will also be a GP only. Even if we divide also, that means a by 2, ar by 2, ar square by 2, and so on, ar power n minus 1 by 2. So even this sequence will also be resulting as a geometric progression. The only condition we have to identify here is either there are only 2 possibilities, either it can be multiplied or divided, and that quantity should be a same and non-zero quantity. So like here we have seen the two examples, two cases here. One is for multiplication and the other here is for division. Right. So this is all about the first property of our geometric progression. So let's discuss the second one. If in a finite GP, the number of terms is odd, then its middle term is the geometric mean of the first and last term. So in the geometric progression, sometimes we might have even number of terms, sometimes we might have odd number of terms. Right. So according to this property, if we are having a finite number of terms in a geometric progression, right, for suppose I'm taking my r equal to 2 and my first term here is 3. That means 3 into r 6 and 2 square 4 into 3 12. Right. So let me consider this. Right. So here this is my GP. Okay. So in a finite GP, your GP should be finite and the number of terms is odd. Then its middle term is the geometric mean of the first and last terms. So far we haven't discussed the geometric mean. So when we are getting into, after discussing this geometric mean, I'll just come back to it. So we have seen our r is equal to 2 and the sequence will be 3 and 3 into 2 6 and 2 square will be 4. So 4 into 3 12. For suppose this is my GP, geometric progression. So according to this, here how many terms are there? Here 3 terms, which means odd number of terms. Then the middle term, that means 6, is nothing but the geometric mean. So geometric mean here is nothing but root over AB. So our arithmetic progression, in arithmetic progression we have seen for arithmetic mean which is given by a plus b by 2, whereas for geometric mean it will be root over AB. So here root over A is 3 and B is 12. So 12 into 3, 36. So root over 36 is nothing but 6. Right. So here according to this property, we can predict it here. That means when we have odd number of terms in a geometric progression and it's a finite geometric progression, then we can directly predict the middle term which is given by the geometric mean of the first and the last term. So here the first term is 3 and the last term is 12. Right. So let's discuss the next property of geometric progression. So the reciprocals of the terms of a given GP also give a GP with a common ratio of 1 by r. So let me take a standard geometric progression. So AR square, AR power n minus 1. So this is my geometric progression with common ratio is equal to r. Right. So if I have taken the reciprocal of all these terms, then my progression will be turning out to be 1 by A, 1 by AR, 1 by AR square, and so on 1 by AR power n minus 1. So this is my new geometric progression which is resulting by taking the reciprocals of the terms which are present in the above progression here. Right. So now the property states that this resulting progression also will be a geometric progression with a common ratio equal to 1 by r. Right. So this is also a geometric progression with a common ratio 1 by r. Right. So that you have to keep in mind. So let's discuss the next property. So if each term of a geometric progression is raised to the same power, so let it be, it can be k or something, then the resulting sequence also forms a GP with a common ratio as r power k. Right. So here if we are having A, it will be A power k, A power r power k. So if our every term is raised to the same power, right? So then our common ratio will also be raised to that particular power here. Excuse me. So that common ratio for that progression will also be raised to that power. So like for the previous, then if we take the reciprocals of the term, the common ratio will also become 1 by reciprocal of it. That means common ratio will also be turning out to be 1 by us. And the same manner, if all the terms has been raised to the same power k, then our common ratio will also be raised to the that particular power, which is r power k here, right? So these are the properties which are related to our geometric progression, which we have discussed. And so far we have started with our series of GP, and then we have discussed our properties related to the GP. So now let's start doing questions related to our geometric progression, that is our sum of geometric progression, which is nothing but series of an GP. So here comes the first question, guys. So read the question carefully and take 2 to 3 minutes and give it a try. So if you guys require more time, like if you want to give it a try, so please let me know before I explain the solution of it. So give it a try, guys. I'll check the comment section. So those who have already finished solving, you can let me know the answer, guys. So those who are having questions, doubts, you can let me know in the comment section. If you require more time, that also you can mention in the comment section. I'll just keep checking the comments frequently, so no need to worry. So here given series is S, which is given by 9 plus 99 plus 999 plus 9999 and so on until some n. So the first and foremost thing here is how can we rewrite this given series? So that's our first thing to have a look here. Because it is not easy to find this typical sum of this given series, that is 9 plus 99 plus 999. So we have to convert this in different formats. So how can we rewrite this given series in an easier way to get the solution? So there will be some relation, right, from these terms which are given here. So here we can see that 9, 99, 999. So likewise, the series has been increasing. So 9 can be written as rewritten as 10 minus 1. In the same manner, 99 can be written as 10 square minus 1. Similarly, 999 can be written as 10 cube minus 1. Right, so that's the common thing which we can see amongst the given terms. Right, so similarly and so on, 10 power n minus 1. So the given series is nothing but 9 plus 99 plus 999 and so on. So that I have rewritten in terms of 10, which is given by 10 minus 1 plus 10 square minus 1 plus 10 cube minus 1 and so on plus 10 power minus 1. So from this given pattern, how can we find this sum? Which means how can we convert this? How can we try and understand in point of view of our geometric progression in order to find the sum here? So now how can we rewrite this again? How can we simplify it? So this can be written as 10 plus 10 square plus 10 cube, and the next will be 10 power 4 and so on until 10 power n, and the others here will be minus 1 minus 1. So these will be until n times, right? So now this will be turning out to be 10 plus 10 square plus 10 cube plus 10 power 4 plus and so on 10 power n. So these all minus ones will be repeating n times, so which will be equal to minus n. So now if we try and separate this as a separate term, so that from that we can identify that which is they are in the our geometric progression. So they are in terms of our geometric progression. So now we can apply our formula of geometric progression, that is sum of the terms, and we can get the answer here. So let me know the answer, guys. So now our geometric progression series is given to be 10 plus 10 square plus 10 cube plus 10 power 4 plus and so on until 10 power n minus n. So quickly simplified, guys, and let me know the answer here. So we know the sum of n terms in a GP formula. We have already seen that. So which is given by Sn will be equal to A into 1 minus R power n by 1 minus R. So this is our formula which we have already seen. So relate that to our given GP and identify what is the first term, what is the common ratio here. Right. So here this is also in terms of n. So there is no particular value for n here which is not given, which means you can directly take that to be n and get the answer. So identify the A value, that is the first term, as well as the common ratio of the GP, and figure out the sum of the n terms here. So let me know the answer in the comment section. No one has given it. So let's just wait for a few more minutes. So just compare this to your regular and general GP and identify the first term and common ratio. So here from this we can identify that this is our first term, which is given by A here. So A here will be equal to 10, and the progression here is increasing by 10, 10, 10, which means the common ratio will be equal to 10. That is, our value is also 10. So now we have identified A is 10 as well as R equal to 10. So let's just substitute that. That means our S here will be equal to 10, 1 minus 10 power n divided by 1 minus 10, and then here we already having here minus n, so it will be minus n. So thus S value according to the given question will be equal to here 10 into 1 minus 10 power n, 1 minus divided by 1 minus 10 minus n. Right, so the given series S will be equal to 10 into 1 minus 10 power n divided by 1 minus 10 minus n. So this will be the final answer here. So let's move on to the next one. So we have just finished our series of geometric progression. So now let's just discuss the geometric mean. So just before I just given a intro to this geometric mean, where we have seen in examples while we are discussing the properties of geometric progression. So let's start with the definition of this geometric mean. So if A, B and C are three positive numbers in GP, right, then B is called the geometric mean between A and C. So if we are having A, B, C, three positive numbers in a geometric progression, then B will be called to be the geometric mean of this progression which is in between A and C, and that is given by, B is given by root over AC. So that B is given by root over AC. That means from here B square will be equal to AC. So we can consider this to be as a condition where B square equal to AC, or we can say in order to find the geometric mean we can use this, where geometric mean B will be equal to root over A square. So it's root over AC. So in the previous example we have seen that 3, 6 and 12. Right, so if these are A, B and C, so accordingly B square should be equal to AC. That means B square is 6 square and A here is 3 and C is 12. So 6 square is 36 and 12 into 3 is also 30. That means it is satisfying our condition, that is B square equal to AC. Right, so that means geometric mean here, if we are having three positive numbers A, B, C, B will be the geometric mean which is given by root over AC, from where we end up having the condition B square equal to AC. Right. So if for suppose we are having only two real numbers of the same sign. So initially we are having three positive numbers, but now we are having only two real numbers which are given by AB. Then the geometric mean between these two numbers is given by G will be the geometric mean. That means G square will be equal to AB. So this is the condition which will be applicable in order to find the geometric mean between them if we have two real numbers of the same sign which are given by A and B here. So here comes the note point. So far if we have seen the two conditions when we have ABC, three positive numbers, and AB, two real numbers of same sign. That means it indicates that if we have two numbers A and B are opposite signs, then the geometric mean between them does not exist. Right, so that means A and B should be of same sign. So A and B must be of same sign. So they must be of same sign. So they cannot be two numbers of opposite signs. So this is the note point which will be very, very important when we are dealing with the geometric mean between any given numbers. So likewise, how we have discussed in our arithmetic mean, like inserting an arithmetic means between any given two numbers. So the same thing will be applicable here. That means inserting some n geometric means between the two numbers A and B here. Right. So can you guys think of it, and can you guys write the sequence of this geometric mean before I just give you the introduction to this? So what happens if n geometric means inserted in between given two numbers A and B? Write the progression and let me know what will be the nth term here, how many number of terms will be present in this geometric progression, and what will be the general term as well as the last term here equal to. So give it a try of this, because we have already discussed the same pattern while dealing with the arithmetic mean in our previous session. So it will be easy for you guys to do it. So quickly do it. I'll be checking your comments. If you have any doubts, you can post there. Come on guys, quickly let me know the sequence here as well as the last term, number of terms present, and the general term here. Quickly. If you have doubts, you can post there. No one has given reply yet, so quickly. Okay, let's just continue. So far, no one has given any reply. So here we are just considering two positive numbers A and B. So in between these two numbers, we are going to insert some geometric means, like how we have inserted an arithmetic means in our previous session. Right, so those are represented by G1, G2, G3, and so on until Gn, and the last term will be B. So now the progression will be having the terms involving here, that is A comma G1 comma G2 comma G3 comma and so on until Gn comma B. So we know that until from G1 to Gn we'll be having n terms, and apart from these n terms we'll be having two more terms A and B. So the number of terms in this progression will also be equal to n plus 2 terms, right? Whereas here A will be the first term of the progression and B will be the last term of the given progression here, right? And now what happens, the sum product of this GP, right? So initially we have seen the sum of the inserted arithmetic means, but here as it's related to geometric progression which is product, they are going to see the product, that means G1 into G2 into G3 and so on until Gn. So this n product, n inserted arithmetic means product will be equal to G power n. So with G we already know geometric mean of two terms, that is root over AB. That means the product of all these inserted n geometric means will be equal to root over AB power n, which is AB power n by 2. Right. So this is how we can easily try and figure out the product of the inserted n geometric means between two positive numbers A and B here. So let's do a question here related to the geometric progression, and then we'll just move ahead with our next concept. So this is a typical word problem type of question. So have a look over this question, try to understand it and try to convert the given words information into our mathematical form in order to make it easy. So quickly try and have a try here. Have a look here.
అన్వర్ చెప్పరా మెసేజ్ పెట్టా చూడు చూడకుండా 8:30 చేస్తా.
So read the question, guys. Try to figure out the progression here, the sequence. So let me read the question. On a certain date, the height of a plant is 1.6 meter. That means let us take some initial point. So 1.6 meters, right? So if the height increases by 5 centimeters in the following year, and if the increase, so initial increase will be, so initial increase will be 5 centimeters, right? And in the following year, and if the increase in each year is half of that the preceding year. So increase in the, so let me take increase in the first year. So that is given by 5 centimeters, and my increase 2, that is increase in the second year, will be half of my previous increase. That means 5 by 2 centimeters. So likewise in my third year it will be increase in my third year will be half of this, that means 5 by 4 centimeters. So this will be going on like that, right? So now the question is, show that the height of the plant will never be 1.7 meters. So here we have to show that the height of the plant will never reach 1.7 meters. So this will be our application part here with respect to our geometric progression. So quickly try and apply this concept here. So the only increase part here is related to our geometric progression. Right, so you can identify this. That means our progression will be 5, 5 by 2, 5 by 4, 5 by 8 and so on until some n terms. So now how can we figure out whether the height will be reaching until 1.7 or not? So if for suppose let us assume that the height of tree has been reached to the height of 1.7 meters. Then what is the increase in the height? So increase in the height, so this is my assumption. I have assumed that my plant has been reached the height of 1.7 meters. If the height that plant has been reached the height of this 1.7 meter, then my increase height will be given by 1.7 minus this 1.6 meters, which is given by 0.1 meters. So 0.1 meters is nothing but 10 centimeters here. Right, that means my increase in the height will be equal to 10 centimeters. So my total increase here is 10 centimeters. That means sum of all these increases will be equal to 10 centimeters or not, because that is the overall increase of my height of the plant. That means my sum of the series, that is 5 plus 5 by 2 plus 5 by 4 plus 5 by 8 and so on until some n terms. So this sum of the sequence, this series will be equal to 10. Right, so if we could get the exact n value here, then my assumption is correct, which states that the height of plant reached 1.7 meters. If I couldn't get this n value here, that states that my assumption is wrong and it will be a contradiction that states that the height of the plant will never be 1.7 meters. Right. So now overall what we have to do, the next simplification step here is 5 plus 5 by 2 plus 5 by 4 and so on until some n terms is equal to 10 centimeters. So this is our present condition. So now we have to try and figure out the n value here. So find the R value, that is the common ratio here, and apply the formula of our sum of first n terms. So here my first term, that is A, will be equal to 5 and R, which is the common ratio, it will become 1 by 2. So now let's equate my sum of n terms, that is A, that is 5 here, 5 into 1 minus R power n. So R here 1 by 2 power n by 1 minus r, that is 1 minus 1 by 2. So this sum must be equal to 10. Right, so let's simplify. So 5 into 1 minus 1 by 2 power n, 1 power n will be 1 only. So 1 minus 1 by 2 will be 1 by 2, which is equal to 10 here. So this will come here, that means 10. In the numerator, 1 minus 1 by 2 power n is equal to 10 again. So this will become 1. So 1 minus 1 power 2n is equal to 1. Right, so now if I bring this, so 1 minus 1 will become 0. So 0 equal to 1 by 2 power n. So how this will become 0? For what n value this will become 0? If I take n 0, this will be 1. If I take n minus 1, this will become 2. Right, that means there is no possible n value such that it holds that the result equal to 0. Right, that means there is no such n value which states that my initial assumption is wrong, which is the contradiction to my assumption. Right, that means the height of the plant will never reach the height of 1.7 meters. That means the plant height will never be equal to this 1.7 meter. Right, so that's how we'll apply our geometric progression concept and our series of GP concept in order to solve this typical word problem here. So let's move on to the next one here. So the next one is, so far we have finished our arithmetic progression and followed by the arithmetic mean, and then we have started discussing the geometric progression followed by the geometric mean. So now we are having the relation between this arithmetic mean and the geometric mean, which is given by arithmetic mean of any two non-negative numbers will always be greater than or equal to the geometric mean. So this is the relation between the arithmetic mean and the geometric mean for any two non-negative numbers here. Right. So let's solve a simple question here related to our geometric mean. So calculate the values of n so that a power n plus 1 plus b power n plus 1 by b power n plus b power n may be the geometric mean of a and b. So this will be the geometric mean. So here we have to figure out the n value. They have mentioned maybe. So that we can assume here, that means my a power n plus 1 plus b power n plus 1 divided by a power n plus b power n. This can be equal to my geometric mean, that is root over ab, that is ab power 1 by 2. So try and simplify this in order to find the n value here. So take 2-3 minutes and give it a try. So how can we simplify this? So let's first do this typical cross multiplication here, which gives a power n plus 1 plus b power n plus 1 here, and the other side it will be a power 1 by 2 into a power n, right, same thing, a power n into b power 1 by 2. and the other thing b power n into a power 1 by 2 plus b power n into b power 1 by 2. So now we'll be having a power n plus 1 plus b power n plus 1, and here a power n plus 1 by 2, and here a power n into b power 1 by 2, here b power n into a power 1 by 2, and then b power n plus 1 by 2. So now we have to take something in common. So that's why in my RHS I can take b power n plus 1 by 2 as common, right, which will be remaining with a power 1 by 2, and then the other will be minus b power 1 by 2. So let me make it easier. So far we have rewritten them in terms of our powers. So now I can bring all my a's to one side and b's to the other side. So that means a power n plus 1 here, and the other a term I'm having is minus a power n plus 1 by 2 here, right? And the other side here I'll be remaining with minus b will be coming here. So a power 1 by 2 into b power n plus 1 by 2 minus b power 1, right? So you can just do the simplification here further. So now it will be, after this it will be turning out to be a power n minus 1 n plus 1 minus a power n plus 1 by 2 into b power 1 by 2, which will be equal to a power 1 by 2 b power n plus 1 by 2 minus b power n plus 1. Just have a look over this, and then from here we can take this a power n plus 1 by 2 common this side, a power 1 by 2 minus b power 1 by 2, and same thing to the other side, b plus n plus 1 by 2 can be taken common, a power 1 by 2 minus b power 1 by 2. So these two will get cancelled here, and we'll be having a power n plus 1 by 2 equal to b power n plus 1 by 2. Right, so now we can rewrite this as a by b whole power n plus 1 by 2 as the power is same. So this will be equal to 1 here. Right, so here anything power 0 right here, that's only the possibility which will be equal to 1. That means n plus 1 by 2 will become 0, where n will be equal to minus 1 by 2. So in the given condition, if my n value is equal to minus 1 by 2, then there is a possibility that that will be equal to my geometric mean. So let's check that by taking n equal to minus 1 by 2 and substitute there. So minus 1 by 2 plus 1, it will be 1 by 2 plus minus 1 by 2 plus 1, that means b power 1 by 2. So here a power minus 1 by 2 plus b power minus 1 by 2. So it will be ending up giving at last equal to root over ab. So the final value here is, we have to figure out the n value, which is equal to minus 1 by 2. So you can check the same question for arithmetic mean also, where you can take a power n plus 1 plus b power n plus 1 divided by a power n plus b power n will be equal to a plus b by 2. So you can take this for geometric mean also, and you can check this for arithmetic mean also and have a try. Right, so with this I'll just wind up our today's session, and we are left with few more concepts in this chapter of sequences and series, like arithmetic geometric progression, that is the combination of both arithmetic progression as well as the geometric progression. So that part we'll just discuss in our next session of sequences and series. So that's all for today, guys. So if you have any doubts in the session, you can let me know. So you can just go through the session once again to make the concepts even more clear. So that's all for today. So let's continue the rest of the topics in our next session of sequences and series. Thank you all.